Okay, so I'm going to do a quick sort of review over from the slides from GIS 201. There's about 450 or so slides from the semester, and I chose not to take any of them out because I left them in when I was selecting exam material. Now here's my recommendation for how you should study. You should look over this set of 450 slides one at a time, read through them, look at your notes, go through everything once. And take a little time away, hour or two, something, come back later, watch this video. Pay attention to the things that I say to pay attention to and go back and study them. Then, after that's all said and done, look through all your slides again. Then take some time off, a day or so, and repeat the cycle. So today's Thursday, so assuming you started on this and you went over it all sometime Friday and then didn't look at it on Saturday, you could go over it again on Sunday, not look at it on Monday, look at it again on Tuesday, and then be ready to take your exam on Wednesday and probably do okay. If you have trouble, look at it more. If you're really comfortable, look at it less. So that's that little bit. Now I'm going to start working through the slides. I'm going to try to cut this down to about 35 minutes or 40 minutes at the most, maybe less. I'm not going to spend a lot of time talking about what's on the slides. I'm going to spend more of my focus on telling you which slides are important. Discrete and continuous, that's important. Know what vector data is. Know what attributes are. Understand what generalization is and how you use it. Know what the definition of quality data is. It's here in bold. Should be hard to find. Let's see here. Sometimes you're going to hear sounds like that when I'm singing to myself as I'm thinking and moving through. It's not going to make sense. Just disregard it and go on. Logical consistency is important. I just want to make clear, because I'm going over these things 100 miles an hour doesn't mean they're not important. It means that there's not something there that's jumping out that I remember writing a test question about. There'll be things that are test questions that I maybe miss. That's why I'm telling you to study everything a little bit and focus more on what I'm asking you in these slides. Okay, now we're getting back into more GIS stuff and less software stuff. Different ways of differentiating things in terms of like what symbology is. You need to know what nominal data is. You need to know what categorical data is. Ordinal data, interval data, ratio data. When we talk about different kind of maps, like class maps, that's always something that you want to know. You should also know about chloroplaths and what a chloroplath is. Understand what the modifiable area unit problem is. How arbitrary aggregation units like states or counties can influence values. We talked about it in class. Everyone looked at me like I was speaking Mandarin or something. We covered this. It was just a while ago. How you minimize it, how you normalize it, and then there's another version of it called visual map and what it actually means. Know the two types of rasters, discrete and continuous, and how they're different. Know what stretching is. I mean, it's basically just reallocating a smaller portion of your values across the 256 shades of color. So you cut the tails and jam them together into a single bin so that you can stretch out the bulk of the data in the middle and get more detail. Classifying data is important. You need to know some of these techniques. Specifically, Jenks natural breaks. You also need to know defined interval or equal interval. You better know some of these statistical ones, specifically quantile, because I'm going to ask you about quantile and Jenks. Shocker, I know. Geometrical, I'm not going to ask about that. Layers, layer file, styles. Okay. Have some idea of this map making process of selecting, arranging, symbolizing, reviewing, editing, and wash, rinse, repeat. Know what cartographic generalization is. Understand what visual hierarchy means. Coordinate systems. Lots of stuff here to talk about. Know about the two main types, projected and unprojected. Know that unprojected are geographical coordinate systems, or a GCS, projected or projected coordinate systems, a PCS. GCS based on spherical coordinates, PCS based on two-dimensional map made by math, used to convert 3D to 2D, creates distortions. When we talk about GCS, typically we're talking about things that are measured in longitude and latitude. You better know what those two mean. Precision's not good. This whole process here, this is one of the essay questions about how we go from that sphere to the spheroid to the geoid to the datum to the GCS to the PCS. And it's not enough just to say you go from a spheroid, from a sphere to a spheroid to a geoid to a datum to a... No. Tell me what they are. Spheroid is a perfect mathematical shape. It's irregular. It's got a short and long axis. We find a spheroid that is similarly sized to the geoid. We adjust the center of one till it lines up better with parts of the other where we're interested in. That gives us a datum. From the datum we can then calculate spherical coordinates on the spheroid. That gives us our GCS. We can then use math to convert that into a 2D map, giving us a PCS. You need to be able to go through all that whole process. Just more telling you about datums. Make sure you understand all of it. The more you know, the better you can explain it. What datums we use in North America, how you choose them, transformations, transformation warnings. Let's see here. Note for GPS users. Yeah. Projections are mathematical conversions of points on the Earth's surface to a flat plane. That's a good way of putting it. Every projection has an underlying GCS, so PCSs are always based on a GCS. Remember that, don't forget it forever. Types of projections. When we talk about types of projections, we're talking about cylindrical, conic, and azimuthal. Know what they mean. Know what standard parallels are. Know about the two sort of flavors that each of the different types of projected coordinate systems come in, that being tangent and secant, tangent having one standard parallel, secant having two, and what that means as far as where they're accurate where the line is, they're accurate at that standard parallel, more so there than anywhere else. No distortions at the standard parallels. Bum bum bum. Yeah, this one you better study. Alright, so I'm going to ask you to explain the UTM system. There's a lot there to explain and unpack, and I'm going to go through parts of it here just to make sure you get it. Number one, it's a cylindrical projection. Number two, it is configured transverse. In other words, not up and down, it runs sideways. By running sideways, the standard parallel intersects on a plane from pole to pole, north to south. As you rotate the cylinder around the globe, the standard parallel moves. There's 360 degrees of longitude or latitude, or whichever one it is, that goes around the planet. If you divide that up into 60 north-south zones, each one is going to be 6 degrees wide. That means that central meridian, or that standard parallel is in the center of a zone, and to the edges of the zone it's only 3 degrees distance, meaning that things within the zone have relatively little to almost no distortion. Distortion only becomes a problem as you get further and further away from that zone. The map on the right down there shows the different zones across the U.S. You should be able to explain to me that the UTM system is a transverse Mercator cylindrical projection where the Earth is divided into 60 zones, each one 6 degrees wide, with little to no distortion within each zone, period. State planes are another system. It's like the other one that we use commonly in the U.S., so we use 3 commonly. A GCS for moving data around and sharing, the UTM system, and then the state plane system. The state plane system, instead of these huge zones, has little areas, often at a sub-state level, where there is a particular type of projection that fits well for that location. Large-scale and small-scale maps, you really need to be able to explain or to understand the difference between the two. I'm not going to go into great detail, but it's all about that, like 1 to 24,000 versus 1 to 100,000. The 100,000 is a bigger number, but it's a smaller scale because the big number on the bottom of the 1 to 100,000 is a fraction. 1 over 100,000 means it's a very, very tiny number, a very small scale. Just make sure you know that. Creating custom projections by adjusting your standard parallels and your central meridians. On-the-fly projection. What do you need to know about this? Data that's in any coordinate system will be automatically converted to the coordinate system of your map, but the conversion does not affect the stored coordinates. It only affects the display, and so it really doesn't convert it, it just displays it as if it was converted. That's why you always go ahead and make all the conversions on your data. But for simply looking at it and displaying it and seeing if it's what you need or what you want, then the on-the-fly projection functions that are available in the ArcGIS software does wonderful things. One of the big problems that we have with spatial data is we have missing information or a missing label. So if we have spatial data that has all the information but it's not properly labeled, we have to define it using the define projection tool. The define projection tool is used when we have to correct an errant label or label something with a missing label. This allows us to then have the data to display properly. Do not confuse define projection tool with project tool. Define projection changes the label, that's all. Project tool takes a set of coordinates with a defined coordinate system and makes a new copy of that data set in a new coordinate system. All new parameters, all new numbers, etc. If it's a raster, you can't use the project tool. There's a special tool, project raster. Vector data, all we love are vector data. Feature classes, spaghetti models, topology models, topological models, store information on how features are spatially related. That is a good thing to know. That's a test question, actually. File extensions. Bum 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 bum. Local garacha. La 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 la. Oh, extracting data. This is important. You need to know what a query is, what a clip is, and what an erase is. These are test questions. Generalizing. Why do we do it? Good question. Probably a test question, possibly a test question, maybe a test question. Dissolving. Again, something you need to know. Could it be a test question? Maybe. Metadata. On the previous slide I should have said, what is metadata? It's data about data. That's important to know. Path names. This is basically how you name files. There is a question about how you name files. Short, descriptive. Less than 13 characters. Don't start with a number. Don't use special symbols. Only use underscores. Don't use spaces, etc., etc. Raster data. Raster data. Oh, how we love raster data. Pixels and cells, same thing. They're synonymous with one another. Why do we use it? Better for some things, faster for others. What are some examples? Here are some. Continuous surfaces, discrete rasters, raster tiles, raster resolution. The resolution of a raster is defined by the x and y dimensions of the pixel. That smells like a test question. Raster pyramids. What are raster pyramids and what are they for? They are built for a raster to speed up its display. They are successively lower resolution copies that are created to make it easier to display things when you're zoomed out farther. Makes your data set 50% bigger. Resampling. Yep, we're there again. Block resampling. Group of pixels, uses a block, doesn't overlap. There's also nearest neighbor, bilinear, and cubic convolution. You better know these definitions. That's a test question for sure. What is a digital elevation model? What is a voxel? FYI. Means those are test questions. Point clouds from LiDAR. Don't think that's on there. Tins might be. I'm not real sure. Anyway, it's little triangles used to make a elevated surface. Just in general, you need to know that attributes are information about spatial data. Understand what joins are. Okay, topology, what is it? Spatial relationships between features. Logical consistency, things behaving in the GIS the way they behave in the natural world. To see intersections, not the tool intersection, but like an intersection on a road. Is it a true intersection? Is it an underpass? Is it an overpass? Etc., etc. Snapping. My mom says I've got snapping good looks. All moms say that. No, snapping ensures that the end of the road of the vertices of the polygons match. Basically, when you're trying to connect things, it's hard to get it exact. So if you get within a certain tolerance, it snaps it together automatically. Let me rewind that and try one more time. Coincident polygon boundaries. Polygons are stored as complete loops. Sometimes those loops share a border. That part of the border that is shared between the two polygons is coincident. And if you set it up to use map topology, when you edit polygon A, the coincident portion of that border that you move will move the coincident portion of polygon B. Map topology enables adjacent or connected features to be edited simultaneously, preserving the correct topology. That sounds a lot like a test question. Let's talk about queries. What is a query? They extract a subset of features, classes, or table based on a condition. Sounds like a test question to me. Some examples, different types. They use operators, attributes, SQL expressions, Boolean things. Here's some Venn diagrams. Who likes Venn diagrams? Nobody. Spatial queries test spatial relationships between two layers. That is another kind of a test question-y sort of thing, isn't it? Know what dissolving means in terms of buffers and what buffers are in general. When we talk about extraction functions, know the difference between clip and erase. Know what happens when you clip and erase things. You change areas, make sizes different. And that means that you usually have to calculate the geometry to fix it. Joins and overlays. How are they alike? How are they different? Okay, quick review. Tables, match up fields. Doesn't have to have the same name, has to have the same information. They join together. Poof! Spatial joins. Data at one location from one data set, data at the other location from the other data set, joins it up based on location. Typically off of proximity or containment. If you're looking for a definition, that would be on a matching sort of question. Spatial join, the records are matched using a spatial relation step instead of a key field. Not saying any of those previous slides weren't important. They're just different examples of different types of the same concept. Classic overlay, multiple layers, different stuff. We bring them together. Most common overlay functions: intersect and union. Said it before, say it again. Test questions. What does the intersect do? What does the union tool do? There's also clip and erase, where attributes are not joined, as opposed to intersect and union, where attributes are. Again, areas and lengths. The geodatabase fields in a feature class, shape_length and shape_area, are automatically updated. User-defined geometry, not so much. Anything in a shapefile, not so much. It's best to just assume, if you do anything to modify anything, that everything's wrong, and just update it. Calculate the geometry to fix it. Raster analysis. Map algebra. Raster pancakes with math filling. That's basically how it works. I just flew past those density function things. There may have been a test question there, so go back and study those a bit. Interpolation, you need to know what this is and what the definition of it is. And so you know, estimates values in between point measurements, that would be interpolation. Various surface analysis that we can do. Slope, aspect, hill shade, and view shade. It's important to know what these things are. Slope calculates the steepness. Aspect calculates the direction of the steepest slope. Hill shade gives this mimics the appearance of a uniform topographic surface under an illumination source. In other words, it puts the shadows on the DEM from a fixed positioned sun. Viewshed shows you what you can see from a certain spot, assuming that the physical properties of the surface of the earth and whatnot block certain things. Neighborhood statistics know how it works. Two types: neighborhoods, blocks, and focal. Understand the difference. Sometimes when we make polygons out of rasters, we simplify. Understand what that tool does. Same way with zonal functions. A reclassify function changes the values in a raster set to a different set of values. Boy, that smells like a test question. I just noticed since I shaved off my mustache, it doesn't rub the boom mic, and it makes doing these videos a little bit easier. Okay. Resampling comes up all the time. If you don't know these techniques by now, you need to learn them. Chapter 12, Sharing GIS. Gonna go through this. There's only a few little bits of things here I want to talk about. Know what metadata is. Go back one slide to web maps. Know what a web map is. Know what a model builder is. Now, there's not a real good written definition here, so I'm going to give you one right now, and this is the one that you're probably going to want to pay attention to for the exam. Model builder is this graphic user interface that allows you to construct GIS models, basically. Alright, let's talk about some of these models. Binary models uses logical expressions. True, false, yes, no, 1, 0 kind of things. index models, we were going to talk a tick about them. Regression models. Index model gives you a ranked map. Index is similar to binaries. Both have multiple criteria. It depends on overlay functions. Index value is not the same as a 1 or 0. It gives you a maybe value somewhere in between. It tells you which locations are better or worse than others. It doesn't specifically say you can or cannot. It doesn't specifically say you should or should not. It just gives you a means of scoring every location to every other location. Typically we do that with a linear weighted combination. We do this by assigning the relative importance, standardizing the values, and then we combine that to calculate the index. You can do it with vector data. Again, indexed, standardized, and weighed. Index values are meaningless. You standardize so that the measurement skills don't overwhelm the output. You weight it because some things are more important than others. Standardizing 0 to 1 is a pretty good technique. Z-scores are also pretty good. There's others, dividing by the range and standard deviation, for example. These next couple slides just show you what some of those calculations look like and what some of those equations are. I'm not going to ask you those on the exam. When you do it in a vector scenario, you get that. We might be just about done here. Raster, it's going to look like this. Input rasters, standardized so that we're dealing with similar numbers. Weigh them based on their importance. Then once we've done that, we combine them to get our indexed values. Regression models relates a dependent to an independent variable. We use it to make predictions and estimations. Two types we typically use are linear for numeric and logistic if we have a categorical dependent variable. Process models, not going to talk a whole lot about that, but if you can explain a binary model, an index model, and a little bit about a regression model, you're in pretty good shape. If you know what those three are, a process model is just something that we soup together out of those other three that mimics some natural process that we know and understand, and that we're trying to represent in terms of a model. Remember fuzzy logic, fuzzy membership. Instead of a yes or a no, a 1 or a 0. Instead of a misting rain or a monsoon flood, it gives you that variability somewhere in between.